Okay, so let's look at some examples. So in our explanation video, we talked about integration and differentiation. So the integration is when we have this little S sign right there. So that means
Okay.
we need to integrate. So remember, with the integration rule, what we had to do is add 1 onto the exponent and then divide by whatever the new exponent is. So let's say that we have here now this sign here, but what I'm going to do is I'm going to times this 4 in. Actually, I don't need to. I don't need to. I can times it in later. I could either times it in first and make it like this. And some people might find this easier, because then you just do each of these individually. 3 times first. So that'll be 12 theta. And then just integrate it. This is a notation thing, by the way. That just means just pop that on.
So that's got no additional value.
No, it's notation, and when we do integration by substitution, which I don't think we have to do, then we would go on to that. We would use that.
Okay.
But I think in 4 we maybe don't have to do substitution, but if we do, then I will show you how to do it. So if I was to do this, we add 1 to the 5, so it becomes 6, and then we need to divide by that 6. So then we have
Then it would be like 4
that's it.
divided by. Okay.
Perfect. Yeah. And then 12. And then we add 1 to the thing, so we can 2, and then divide by that 2. Okay, so let's just see what we did there. So notice that we add 1 to each of the exponents. So 6, 4, 2. And then we just put those values at the bottom. 6, 4, 2. So the other thing is I times in the 4 in order to do that. But what I could have done is I could have done these each individually. And you see that I would have got the same answer. And then I would just times the 4 in later. But as it stands, I times the 4 in first, and then did them each individually. So whichever works for you. 2/3 theta to the 6. The 4's cancel. And then it's 12 divided by 2 is 6. The square, that's done. Okay. So what I did there was I times the 4 in to make it easier. Let's see if I didn't times the 4 in. Well, what I would do then is I would do this individually. So let's just write it out again. I would say that would then be 4 times theta to the 6, add 1 to the exponent, divide by 6, theta to the 4, divide by 4, theta to the 2, divide by 2, so 3/2. And then after that, then I times in the 4. You see 4 times 6, we get the 4/6, the 4's cancel. So you then just times your 4 in later. So if you look at that method and find that that's easier than this top method, then you can do that. Doesn't really matter. Get the same answer. So that is called the indefinite integral, because I didn't sub in any values for theta. I just left it as a formula. And so that was the indefinite integral, because I didn't define a region that I need to find the area of. I just found a formula for the area. 3.2 is what we call so let's just say notation here. This means indefinite, because I haven't got any numbers there. And this here is definite, because I've got a definite value here. So this is called the definite integral. Because I've defined the region that I have to get the area between E and 1 over E. Now those are just numbers. Okay, so what I want to do here is get the region, get the integral first, and then do the region. So p squared. What I want to do here is actually get it in a format more like the top one. So what I can do is, if you have 3 over 2 plus 4 over 2 plus 6 over 2, right? Let's just say that 3 plus 4 plus 6 is
What can I separate each one?
yeah, that's it. Okay, I don't have to explain. Yes. So I can separate. So I'm going to say p squared over p plus 2p over p minus 1 over p. So okay, I'm going with, so if it's over a single value, you can separate them into each individual one over that value, right? So what's p squared over p is just p. 2p over p just is 2. And 1 over p. So I'm actually finding the integral of this dp. dp is change in p, because the change in p is that, so the integral is yeah. Probably shouldn't go into that, but that just means change in p, and that's when you find the area, because change is the derivative, and so when you're finding the area, you finding the derivative of the change. Okay, so now p, we just add 1 to the exponent and divide by 2. So because dividing by 2 is the same as saying a half times. Then any value which doesn't have a p just becomes that value times p. Because if I imagine that there's a p to the 0 here, because anything to the power of 0 is 1. If I added 1 to that p, that 0, I get 1. And if I divide it by 1, it's the same. So now this negative 1 over p, I'm actually going to write as p to the minus 1. Okay, from your exponent laws, 1 over p is equal to p to the minus 1. You have to know that. So if I add 1 to minus p, I get p to the 0. And if I do, then I would and then, oh, that's tricky. You can't divide by 0. That is lim. This is a rule. This is lim p. Yeah, so let me just go through that. What was going on in my head there. So p minus 1 plus 1 would give us p to the 0. And then I divide by that new value and I get an undefined answer. So I have to go to my formula sheet and find out what is p to the minus 1. Well, that should be the derivative of p to the minus 1 is ln p. Not the error here. Yeah. So k over x, x is at the bottom. So it ends up being ln. So what did we have? We had minus 1 over p. So p is like the x. So your k is minus 1, your x is p, and so you end up having minus ln p. So in other words, 2 over x is equal to 2 ln x, the derivative. I mean the integral. Okay. Okay, so go to the top. Oh, there. So this is a minus ln p. Now I realize why they gave us e as our value. So now I want the region, so that is the integral from, we want it from e to minus 1 over e. So what I would then do is substitute in e for p. So we'll do a half e squared plus 2 times e minus ln e. That's the first region. Minus, so we'll do that in. So what I can do is just to show you, when you go to, when you go to higher institutions and that, they may even do it here. If I put square brackets and just do that and that, that's telling me that I need to find the value of this from e to minus 1. So this is just again a notation thing. So I'm then subbing in e first for p. So let me just highlight that so we can see what I'm doing. So everywhere we see a p, we are going to put an e. So everywhere there was a pink, and then what we're going to do is everywhere we see a pink, we're going to put a yellow, because we need to go from e all the way to 1 over e. And so we say minus, and then let's put in a bracket here, a bracket here. And so we have a half times 1 over e squared plus 2 1 over e minus ln 1 over e, which is the same as saying e to the minus 1. There's a reason I'm doing that, by the way. So close the big bracket. Okay, well, these values you can put in your calculator. I'm not sure in the memo if they want it in terms of e, but let's simplify this. So it's a half e squared plus 2e. Now, ln e, if you stick in your calculator, should give us 1. Because ln is the same as saying log e to the e. Yeah. So ln e is just 1. You just know that because if you got the e button, you should have an e button on your calculator. So you just put ln e on your calculator.
Okay, I see it.
Okay.
It's e to the power unknown.
Cool. Yeah.
Is
So
that the same thing?
yeah. So if you just say ln that button, and then your unknown is 1, because it's to the power of 1, you should get 1 for ln e. Minus 1 over e squared plus so minus 2 over e, and this ends up becoming plus 1 because ln e to the minus 1, you're using your exponent laws. The minus 1 goes to the front, and so it becomes minus 1 times 1 is plus 1. So this ends up becoming minus 1, plus 1. Oh, I forgot a huge issue, but it doesn't matter in, but, well, it does matter quite a lot. But whenever you find your integral, you need to put just plus c. Now, when you
Plus c.
yeah, because there could have been a constant. So what's the value? What's the derivative of 2 is 0 because there's no x. The derivative of 3 is 0 because there's no x. So there could have been a number when you found your derivative, which came to 0. And that number that it could have been is a c. So we just say plus c because there could have been a number when we, but we just don't know what it is. So we just say plus c.
Okay.
So for this 3.1, our answer there, we had to say plus c. And here we just need to say plus c and plus c. And because what happens when you find the definite integral is your c's go away because you're minusing. So the c's always cancel. So you never have to worry about the c's, but you have to put them in. So you don't have to worry about getting, and it does not plus c because they go away. Because it's that, and that, and so you're saying your c, you're going to minus, let's see, end up minus it. But just pop in a plus c there. So I could just say here plus c and then minus c if I wanted. And so I end up with a half e squared. The ones go away, plus 2e minus 1 over e squared minus 2 over e. And I can put that in my calculator, but they probably accept it like this. Okay. So I think that's good for now. We can do this, the graphing and how this all relates to graphs later, and we can do this also a bit later.
Okay.
This is now.
Yeah, I think give me a chance to like let this settle in, and then we'll take it from there.
Yeah, perfect. Okay. So
Okay.
stop recording there.
Thank you.